Okay, so for steps 5 through 7 of this dynamics project, we were asked to calculate the force on each profile from the additional air mass, from the addition of the air mass, view chapter 14 for calculations. So I went ahead and watched the videos, and the first video is just you setting up the wind tunnel and getting the calculator plugged into the anemometer so you can make your measurements on velocity and force as it pertains to the profiles that you were putting in the wind tunnel to measure drag force. And so these subsequent videos are just you setting up the profiles in the wind tunnel and then using the force sensor and C-clamping it to the table so you can get accurate measurements of force. And the previous videos are for velocity measurements. So you put it into a Excel spreadsheet, and I took that data and I went ahead and solved number 6. So I found that the force is equal to the mass flow times the change in velocity, where the change in velocity is the entrance velocity minus the exit velocity, which is normal to the face of the profile that is hanging in the wind tunnel. So the wind comes in and hits the profile normal, and then the drag force is calculated that way. So this is drag force. And then we know that mass flow rate is equal to density times area times volume. So we end up getting a velocity cancel out because this is normal, and so it hits the face and then the air stops, right? So the velocity becomes 0. So it ends up just being drag force is equal to the density of the air times the area of the cross-sectional area of the profile times the entrance velocity squared. So for the sphere, you can see I use 1.2 kilograms per meter cubed for the density of air, and 1/4 pi d squared for the area of the sphere, cross-sectional area of the sphere profile. And then your first velocity data point is 1.1 meters per second. Square that, and then you get 0.00163 newtons. The units become newtons once you do some dimensional analysis. And so I went ahead and calculated by hand all of the forces in newtons for all of your data points based on the formula here, and I found that almost all of the forces are higher than your measured forces from the Vernier force sensor. And my hypothesis is that it's because the profiles were oscillating like this in the wind tunnel as the force sensor was holding them in place. And so I think that kind of made it so that the air wasn't hitting the face. It wasn't hitting the face the same way every per time interval. And so that kind of threw things off a little bit and made the force seem less than what it actually is on those profiles. And then so for number 7 says create a linear function of the measured force data, force versus velocity, for each profile. So I used, at first I thought I could use a point slope formula, but I figured that's not super accurate. So then I figured out I could use a least squares method using all 4 of the points. So force is equal to A times velocity plus B. So A is equal to the number of data points times the sum, the velocity times force, and then you can see this formula is quite large, but I calculated the values for the sphere by hand. I got A equals this value and B equals this value, and so I wrote that down over here, but I figured this method was a bit too tedious, and so I would just utilize the tool, the glorious tool that is Excel. So I came over here and I used Excel to just plot what's going on with this force versus velocity linear fits of the data for these profiles in the wind tunnel. So you can see the sphere, the equation came out to be 0.0046x minus 0.0065, which is the same as what I got from the least squares method. So you can see that these force versus velocity graphs for the profiles in the wind tunnel are actually pretty linear. They're almost completely linear, actually. And I found it interesting that the R squared value for the large blocks face in the wind tunnel has the lowest R squared value, considering I figured it would be the most linear, but I guess it's not. That might have been a measurement error or something like that. I'm not quite sure, but I thought that was interesting. And so yeah, these are all the equations for all of the profiles in the wind tunnel, and that concludes this video for steps 5 through 7.